Hello, this video is meant to show the steps necessary to do basic time series analysis. Like, what do I do when I'm first given some time series data and I'm going to be doing some work with it? What are the things I always want to start out with? We're going to use an example using U.S. real gross domestic product data quarterly from 2002 until the end of 2024. In our example. There are basically 6 things that you typically want to do with a time series. The first is, really try to figure out what it is that you're doing with the time series. So your objective is pretty important. Are you going to be doing some sort of regression analysis? You have multiple variables and you're doing some sort of time series analysis like that? Or are you going to do forecasting, or are you just trying to decompose the time series into its parts because you're interested in one particular one or not? If you have a multivariate time series, what are the particular variables that you're interested in, and so on. In my example case, I'm not going to be that specific about my objective, but let's imagine that we're either going to be forecasting with the data or just trying to look at its component parts. Maybe I'm going to be using it as part of a multivariate series. I don't know. I just want to understand this time series better right now. The data collection preparation piece, we're pretty much going to skip over for this case. The data collection, this came from the Federal Reserve data set, FRED. I was able to download it from the website. I understand that it is quarterly data because that's how U.S. real gross domestic product data is collected and evaluated. I do want to make sure that the data, anytime I have a data set, make sure that it is complete and consistent. In this case, it is, again, because I know its source, and when we look at time series plots in a minute, we'll see it. But I do want to make sure that, for example, the same variable has been measured in the same ways throughout the time period. That's very important, that something hasn't changed fundamentally about how the data is collected or measured. Again, with my U.S. real gross domestic product data, I'm not concerned about that. Step 3 is cleaning the data. Again, this isn't going to be a big issue for this particular data set because it is a complete data set. There are no missing values, and outliers are rather important. There is a particular outlier that we will see when we look at this one. But generally, in this case, I'm interested in the outliers because of the type of data that it is. If you do have missing values in time series data, it is pretty important to think about how you treat them. So that's one thing I will say a few words about. With cross-sectional data, you can often just eliminate or ignore missing values as long as you have a big enough data set and there's nothing particularly, no particular pattern to which data's observations are missing. You can often just ignore those missing values without really any loss of generality. In time series data, on the other hand, particularly if I'm going to be doing certain types of analyses, I need a complete time series. So if I have holes in the time series, I don't just want to leave them out because it could, affect my seasonality, or could affect how I apply like a moving average type model or something like that. So oftentimes with time series data, when I have missing values, I don't want to just delete them. Instead, I want to try and guess at what they are. Right? So I use some form of interpolation. For example, so I take the values on either side and average them, or if there's a clear seasonal pattern, I would take, the season, the observation from the same season before and the observation from the same season after and average them, or something like that. So you'll want to be consistent in how you create values to replace missing values, and of course document what you've done. So that takes us to our actual exploratory data analysis, which is what we want to do with this time series. So I'll walk through some steps in R, and I will provide this data set and this R code so that you can play with it and repeat it if you like. Of course, there are multiple ways to do some of the things I'm going to do in R, but I'll show you one way and talk about others as we get there. All right. So there are a bunch of packages which I'm going to rely on. I've already mounted all of these in my version of R, but if you haven't, Lubridate, Lippler, Zoo, T-Series, Forecast, ggplot, and TSA are useful ones that come up in this particular set of R code. So make sure you've installed those packages and then mounted them with the library command before you get started. So it's an Excel file that we'll be using for our data. You'll use the read Excel command to bring it into memory. I'm just calling it df for data file. You would want to change the file path, of course, if you're using this R code to bring it into memory. So what does df contain right now? Df is simply two columns, one called date, which has year, month, day in it for each quarter, and the value of United States real gross domestic product in billions of dollars in the second column. So we're going to make some changes to this data set first as we get started. These aren't absolutely necessary, but they'll just make a few things that we're going to do as we go on a little bit easier. So first I'm going to convert that date column into actual date data that R recognizes using the asDate function. And then just for convenience sake, I'm going to create a separate year column and a separate quarter column in case I want to use those later on. So this will make the process of creating dummy variables for quarters a lot easier, or it'll allow us to pick out certain years in the data set and things like that. So I'm just going to create within the data file df a new variable called year that is the year part of the date variable we just created, and one called quarter, which is the quarter part. So after doing that, you can see now that the data file contains two new columns, year and quarter. Nextly, this next piece is, again, not absolutely necessary. I actually know the starting date and quarter of my data set, but if you do ever have data and you're not sure, you can actually query what it is. So I can create a variable or a object called start year, which is just the first observation. That's what the ones in square brackets indicate, and start quarter, which is the first quarter. And then I can use these in my next command. So I'm going to use the forecast package and TS style objects in this R code instead of Sybil objects. Again, just because I'm happy with these commands and know them, and it's what I started doing today when I did this. We could do all of this with the tidyverse code as well, just as easily. So I'm going to convert that US real GDP column into a TS object, which I'm just going to call US real GDP. So again, TS, the variable I'm using, a starting point, start year and start quarter. I could just put 2002-1 in here instead of start quarter and start year if I wanted, and frequency equal 4 because this is quarterly data. And then if I just want to check to see what ends up in my US real GDP time series, then I can see it is in fact quarter 1, 2, 3, 4 for year 2002, and so on and so forth. If I want to check to make sure, is this TS data? Yes, it is. It is in fact TS data. And now I can plot my time series. And I can do this with plot or auto plot, whatever I'd like. But there's my time series. So immediately when I see the time series plot, I can see a bunch of things about it. Maybe this wasn't the best time series to pick because a lot of the things are so obvious that, it's not really necessary to do some of the tests and analysis I'm doing because it's just so obvious. But nonetheless, sometimes it helps that it's obvious. So if I look at this time series plot, I can immediately see the components that it has. It clearly has trend. There is a positive trend, which looks relatively linear over this time period, the 2002 to 2024 time period. There is very clear seasonality. There's very clear quarterly seasonality in this data. And there's some noise, right? There are some big noises that we can point out, the 2008 financial crisis and the COVID pandemic. But there's also noise in each and every year's observation because they're not all exactly the same. And of course it has level because it's not starting at 0. So this time series has all of the usual components. And that means that if I wanted to do some sort of analysis with it, I need to understand those components well. And that's what we're really going to do. So again, I used plot there. I did put in auto plot here just so you can see the difference. Sometimes I like the look of the auto plot plots a little better. Maybe they're a little prettier. I like the grid in the background, for example. But it's just your call, whichever one you want. With any data set analysis that we want to do, of course, we always want to look at summary statistics. So the summary command in R is a good place to start. So if I just do the summary statistics for the real GDP time series, I can immediately then get, mean, median, and the the quintiles in the data set. Honestly, this does not tell me all that much. What does it tell me? Well, it tells me it starts at 3501. That's the lowest observation. It ends at 6001. The average value is, 4,600 roughly. That doesn't really tell me a whole lot. When I have time series data and I'm going to look at summary statistics, I typically want to always break my time series down into interesting parts. I don't know what those interesting parts are. Those interesting parts may very well be different depending on what the time series actually is. So, if, for example, there was some sort of policy change or particular events that we think things were different before and after, then I would definitely want to do summary statistics in those different time periods. If nothing else, we might want to break down our time series into, some sort of roughly even chunks just to see what's going on. So with my real GDP series, I've just decided to break it down by decade and see what's happening by decade with real GDP in the United States. So I have used that year variable that I created in the data file to create a new variable which I call decade, and I'm just defining decade as 2000s, 2010s, or 2020s. Anything before 2010 is going to be the 2000s, and so on and so forth, right? So I just create this new variable called decade that I can now use to look at my summary statistics. Again, now I've added this decade variable, which is equal to one of those three options. And then I want to compute summary statistics for each of those decades. So I'm going to look at, again, mean, median, minimum, maximum, and standard deviation or variance. I want some measure of, because I think if anything is interesting in this particular data set, it might be interesting to see if there is a difference in the sort of, variance or spread of real GDP in each of these decades. If I had the whole U.S. real GDP series going back to the 30s or 40s, then it might be really interesting to look at this, but I didn't pull all of it. So again, this one's just going to create the summary statistics grouping by decade in R. And then to display that, I'm just going to say print summary statistics. So what do we come up with? Again, looking at the means, it's not terribly, and medians, it's not terribly surprising. This doesn't really help me or tell me anything at all. Looking at the graph, I see that there's a clear positive trend, so it's not surprising that the mean value in the 2000s is less than the mean value in the 2010s, which is less than the mean value in the 2020s. What might be a little interesting is that there is a bit of difference in the variance in these time periods. It appears that in the 2000s period, the time period before 2010, there was slightly less variance or variation in this time series. There's more in the 2010 period and a little less than that in the last period. These aren't huge amounts, but looking at the graph, I can sort of see this. The variation here in the early period in the 2000s is somewhat less than certainly what happened in the 2020s, and somewhat, towards the end of the 2010s, there was quite a bit of variation, which I think is probably what leads to the bigger number here. However, we have to remember that this data has seasonality, so a fair amount of that variation is due to the seasonality. So the real question here is kind of like, is the seasonality changing over time? That is it getting bigger or not? So this does sort of tell me that the size of the seasonal swings may be getting bigger over time, and that might tell me the type of seasonality that we have. Okay. And that leads us to the next thing that I want to look at. I want to actually decompose my time series into its component parts so that I can look at them individually. I could do this a couple different ways, and different pieces in the code coming, I'll do them different ways so you see it. I could use the linear model command, and I could create a linear model with a time variable and dummy variables for season. for example, to pull out those components. Or I can use the decompose command in R, which automatically creates a trend and seasonal and whatever's left over component in a time series. So decompose takes one particular argument, and that is whether the seasonality type is multiplicative or additive. So you can try either of them and see what happens. In this case, again, because of what I see in the changing variance or changing standard deviation in this data set, and just looking at the time series plot, to me it does look like the seasonal variation is getting a bit bigger towards the end of the time series from the beginning, and that's an indication of multiplicative seasonality. So I'm going to use the multiplicative argument here. I would probably, if I was doing this for, I'd probably try both of them and see how much difference there is. Turns out there's not a big difference in this particular data set, but it's worth trying. Okay, so we're going to create an object called decomp, which is the decomposition of this time series plot. And if we look at that, just so you know, decomp contains several pieces. X is just the original data. Seasonal is the seasonal component, so it is the these are the coefficients that would be on the dummy variables for each of the seasons. So this is how much variation I expect to see seasonally. The trend, this is the linear trend added to this model. It's X minus the seasonality, if you will. It's the piece that's left over. And then the random component, what's left that can't be explained. And we can autoplot this. So autoplotting your decomp, since it has each of those components, is going to create a plot of each of those components, which is sort of nice. So here's the original data set. Here's the trend piece of the data, just what's the average increase over time, the seasonal component, and then what's left over. The what's left over is a particular place where I could look for outliers in my data beyond just looking at the raw data, and I can see these big outliers right here. Those, of course, are the ones associated with the COVID pandemic. Okay. If I want to use any of these components, I can, right? So since they are pieces within that decomp object, I can simply call trend out of decomp and do something with it. So if I just want the trend piece, I can use it. If I just want those seasonal components, I can use it. They're just called seasonal, and so on. So if I do this, this will just plot that one trend piece out of the data set. So the decomp is useful, and you can then use the components out of it, just like you had done a linear model piece. So speaking of linear models, let's go ahead and try different trends, or at least one trend in this model, because this is something I might want to try to do, to try what happens with different types of trends, and if I want to subtract different types of trends from my variable or from my data series, I could do that. So what I'm going to do is first create a time variable in my data file. This is even not the sequelong. We'll just create a sequential time index. So it'll be 1, 2, 3, 4, 5. So I can say create that time variable. And now again, going back to data file, I now have time, which is just equal to 1, 2, 3, 4, whatever. And then I can fit a linear model using the lm command that is just time. So the linear model is just going to be my raw data as a function of that time variable. And of course, this is going to be highly significant, of course, because there's a very strong trend in my data. So I see that on average, the data series increases by $23 billion per year and starts at $125 billion. And again, not surprising that that's very significant, has a high R-squared. Let's add the prediction, or let's add the linear trend to my data file. So I'm just going to use the predict command from my linear model. This will then use that time variable to create the values of the trend, right? So looking at the data file now, I have, this is where it starts, plus 23 every period, basically. And then, of course, I could plot my raw data along with that linear trend to compare. And here's my raw data in blue and the linear trend in the dashed red line. And the linear trend actually seems to fit this pretty well. This is, while GDP over a long period of time in the United States certainly has an exponential trend, the linear trend, at least through this time period, actually seems to fit pretty well. Again, you might want to try both and see if there's an advantage to choosing a quadratic trend or something. Okay, so that's trend analysis. We've looked a little bit at seasonality. We know it exists. What are other important things to look for in my time series? Stationarity is another clearly very important thing to look at. Clearly my time series, my US real GDP time series, is not stationary. It has this very strong positive trend, and we seem to think that it has multiplicative seasonality, so the seasonality is also changing over time. So yeah, it's not going to be stationary, but let's explore a few ways that we could look at the non-stationarity of this time series. Let's do some graphical measures and statistical measures both. So I'm not sure that in class we talked about using roll mean as a way of looking at stationarity, but it is a common one to do. So roll mean just gives a rolling average in a time series, and if the average is increasing over time, then this time series is going to have a trend and therefore be non-stationary. If the average isn't really increasing, then it's not. So we already looked at means in different time periods in this data set, and we saw that they're increasing, but here again is just a graphical way to do this. So let's plot our raw time series the original way, and then add a line that's equal to roll mean, and I'm just doing the annual one, so k equals 4, since this is quarterly data. I'm going to use k equals 4 and use the middle value as the mean. So if I do that, I get the rolling average of the time series over this period. And again, it's pretty clear that it is increasing. We know it has a positive trend. We know that first differencing is a way to deal with trends, particularly linear trends. So I would typically want to compare this to what happens with first difference data. So if I difference the US real GDP series and then look at the roll mean of that, let's see if that also has the series. So that's the plot of the first difference data and adding the roll mean. Again, I see that this one does not really seem to increase much over time. So it looks like the first difference data has at least dealt with that one type of non-stationarity in this data set, the fact that it has a positive trend. Again, if I want to prove that statistically, the augmented Dickey-Fuller test is the typical way to do that. So ADF.test is the R function. So I'm going to do the augmented Dickey-Fuller test for my original data, and the alternative hypothesis is that the data set is stationary. The null hypothesis is that it is non-stationary. I get a p-value in that test of 0.86, so I cannot reject the null hypothesis, and of course would conclude that my US real GDP data set is non-stationary. If I look at the first difference data, I could do the same thing. If I do the augmented Dickey-Fuller test on the first difference data, then I find a p-value of 0.01 or less, and in fact would reject the null hypothesis and conclude that the first difference data is stationary. Other ways we can take a look at patterns in our data set would be to look at the ACF and PACF plot, the autocorrelation function plots, and the partial autocorrelation function plots. Again, this is another way to see whether there is a relationship between one observation and the observation that follows it, or one observation and the one before it, however you want to think about that. So if I do the ACF plot for my raw data, not the difference data, for my raw data, I see lots of values that are well above the 0.2 range, right? So lots of values that are really high. All of these positive values, again, indicate that positive trend in my data set. The series is very highly correlated with the observation right before it. It's highly correlated with the observation 2 before it, 3 before it, 4 before it, 5 before it, and so on and so on and so forth. So again, this indicates non-stationarity, and it indicates a positive trend. If I look at the partial autocorrelation function, that would be the these are cumulative in the autocorrelation function. If I look at the partial autocorrelation function, again, I see really high first correlations, so observations are highly correlated with the ones that precede them and follow them. But I also see then every fourth observation has a relatively large spike, particularly that first one. This is an indication of seasonality in my data. Okay. Again, I have calculated first differences in this data, so I could look at the same thing with the first difference data to see whether the first differencing deals with the problem. Looking at the autocorrelation function of the first difference data. Now I don't have those every single period big, but what I do see is particularly every fourth one having a really large positive correlation. Those really large positive correlations in every fourth period, again, are indicating that the seasonality is still an issue with the first difference data. And similarly, in the partial autocorrelation function, I see the big four, every 4 periods that I have these relatively large spikes. So clearly, the data has a positive trend associated with it, so I need to look at differences in some way to deal with that. But I also need to deal with the seasonality in my data set. So finally, as the last thing to do here, let's try to figure out how to deal with our seasonality. So again, we did that decomposition command before. One of its components is seasonal. So I can deseasonalize the data very easily simply by taking the data, the US real GDP data, and dividing it by that seasonal component. If I divide each observation by the seasonal coefficient, then that will deseasonalize the data. So I'm going to create a deseasonalized series. And then if I would plot the deseasonalized series against the original series, I should be able to see that, yeah, there it is. So the original data is this should have picked a different color because these look almost exactly the same. The original data is obviously the one that has the up and down seasonal component associated with it. The deseasonalized data is lacking in that. It just has the positive trend. So now what I would hope, right, if I deal with both the seasonal component and the trend component in this data, I end up with something that truly is stationary in all senses. And let's see. So let's create first differences of the deseasonalized data and then plot those first differences of the deseasonalized data and see what we get. That looks like a time series that, kind of has dealt with all of the components, and this is the sort of leftover piece, if you will. So now we can, again, just make sure we can do an augmented Dickey-Fuller test on this data and see. And in fact, yes, once again, the augmented Dickey-Fuller test on the now deseasonalized first difference data is in fact, very p-value of less than 0.1, which means we can reject the null hypothesis of non-stationarity and conclude that it's stationary. And if I look at the ACF and PACF plots now, everything is within those 0.2 bounds. So I really do not have now any significant autocorrelation between these data sets. All right. So hopefully that gave you some idea of some things to look at in dealing with a time series, right? So what are we doing with it? Where's the data come from? Make sure it isn't missing values or we've dealt with missing values. Plot the series, look at summary statistics, decompose the series, check stationarity using a variety of different methods, roll means, statistical tests, looking at ACF plots, and then try to figure out the patterns that exist in the data, trend, seasonality, and those autocorrelation plots. This is a great way to start with any data set that you happen to have, and I hope this helps. Please let me know if you have questions.